Welcome to our great webinar we have lined up today. This is how to reduce costs through energy demand management. I'm Shannon Wetzel with Modern Casting Magazine and American Foundry Society. The webinar is presented by PowerIT Solutions. A few housekeeping items before we get launched into the webinar. We will be taking questions at the end of the session. You can pose those questions by typing them into the chat box in your dashboard. The webinar is going to be recorded and emailed to you within about 24 hours of today's session, so you'll have that for future reference. And without further ado, we'll hand it over to our smart guys at PowerIT Solutions.
Great. Well, thank you, Shannon. Appreciate that. Hello, everyone. Thank you for joining us. My name is Jared Burke. I'm with PowerIT Solutions, and I've got the honor today of having Dick Winsemius with us to talk a little bit about his experience with energy demand management. Before we get started here, I want to just give you a very quick high-level overview of who PowerIT Solutions is.
Okay, hang on a second, Jared. There we go.
Great. So PowerIT Solutions is the leader in industrial demand management. We've been providing industrial energy management systems since 2003 here in North America. We've got over 190 installations who are using our system to reduce their electricity costs as well as manage and analyze their energy spend. Of those 190 customers, a large portion are metal foundries who are melting metal with induction. With that, I'd like to introduce Dick Winsemius, formerly plant engineer for Canon Muskegon, and he's going to be providing this talk today. So with that, I'll hand it over to you, Dick.
Good morning, everyone. I'd like to start out with just a brief overview of the facility I was responsible for. It was Canon Muskegon Corporation here in Muskegon, Michigan. We were a facility that manufactured stainless steel, nickel-based, cobalt-based, chrome-based, and super alloys for the aerospace, medical, and commercial industries. Our typical power consumption capabilities with our connected loads, if all of our furnaces were on simultaneously, we would have about a 10.5 megawatt furnace induction load, plus another 2 megawatts of support equipment within the facility. We operated all coreless induction furnaces. We had two Inductotherm 10-ton melt units. They were 3,600 kilowatt power supplies, and we had them limited through the controls, Inductotherm controls at 2.7 megawatts. And then we had 4 vacuum induction melting units that were coreless induction, a 2 megawatt power supply, a 1.5, a 1 megawatt, and a 0.6 megawatt. As plant engineer, I was challenged to save the company money on an ongoing basis. And one of the first challenges that we took on was making sure that we had our facility set up for the proper sales tax. Through sales tax, we were able to exempt all areas of the plant that were related to industrial processing. For you guys that aren't familiar with that ruling, basically your incoming material or your receiving dock, your shipping dock, and the office areas are classified non-industrial manufacturing. The rest of the plant used to produce metal, process it, and get it ready to head to the shipping dock would be considered industrial processing, and those areas are exempt for sales tax, not only on your electrical spend, but your natural gas spend and potentially lift truck spend. The next area that we attacked as electrical costs started to rise is we started looking at how can we run our operation most effectively to save money from an electricity standpoint. And that was to go in and shift our people, which was a big inconvenience, to the off-peak hours. At the time in Michigan, part of the year would be working at night, part of the year would be working during the day, and we found that cumbersome. The other thing that we found when we shifted to the off-peak, we would find that we would have a capacity charge that we would have to live with, and if we exceeded the time of day for the off-peak hours, we would get into the peak demand charge. Another item that we participated in later, and we'll cover it further in the presentation, was interruptible power. So to give you a little overview, off-peak is the time of day when power is the cheapest for the utility to produce. The capacity is the amount of capacity the utility has to have based upon your highest usage. The on-peak is generally set up during the high-use time periods. This time of year, it would be, falling into the late afternoon, early evening time period because of heating and lighting and it getting darker out. During the summer, it would be more midday because of air conditioning load. A partial or mid-peak, which some facilities face, would be an increment of power usage between the off-peak and the on-peak, and they would call it a mid-peak, and there would be a three-tier pricing structure. The common calculations are time of use, which would be seasonality based for on-peak and off-peak. Typically that would change during the winter months, summer months. Coincidental peak, you'll hear me talk about that. That is when all of your primary loads happen to reach the peak usage simultaneously. There's declining blocks of power, which would be someone who might enter into a contract agreement where they agree to buy, let's say, 1,000 kilowatt hours of power at a given price, and then anything above that 1,000 hours of use would drop to a little lower price. There's interruptible blocks of power. That would be a program that a company would sign up with, and if the utility was reaching a point where they were reaching capacity on the grid, they would ask you to reduce power. Sometimes that information would come to you the day before based upon the weather forecasts. Other times they may give you a 10-minute or a 15-minute window of warning that you would have to be reducing your power. And then the last way that they calculate demands are ratcheting blocks, where you may have a price range for 500 kW, a price range for 1,000, 1,500, so on and so forth. And then as you would exceed, let's say you were in the 1,000 kW, but if you exceeded that, you would ratchet up into the 1,500 kW block, and then you would be responsible for the next 12 months of paying for a portion of that from 1,000 to 1,500 because they would have to have it available for you even if you weren't using it. Typical utility bill that I would see here in Michigan, you can see there's multiple line hours on it. The kWh is the actual energy charge, which is based upon total number of kilowatt hours. The kW would be the charge that you would be paying for the particular period. You can see here the maximum demand charge. The maximum demand charge for a facility was calculated by the highest 15-minute period on any given day during the week. They would take that, multiply that 15-minute of usage out into an hour time block, and that would set the maximum demand for the capacity of the plant. In this case, you can see 1,823 kW at $2.09 per kW. that charge, once you set the maximum demand charge, you live with that charge for the month you set it, plus the next 11 months before it goes down. So for facilities that are operating off-peak, you may have that maximum demand charge, and you are paying a penalty even though you don't realize it. The next item, the big hitter here for us at Cannon-Muskegon, was the on-peak billing demand time period. And you can see we were charged $14.80 per kW, and that was a time period when this bill was taken was from 11 a.m. in the morning until 7 p.m. in the evening. So the highest 15-minute period would be calculated out to an hour charge. You can see it was $17.42 for the month. So we paid $25,000 in demand charge during that time period. This is a generic bill. These are not real numbers. Our demand at Cannon-Muskegon was more up in the 6,800 kW range for maximum demand, and our on-peak billing was typically in the 57 to 6,000 range. So we were being challenged to reduce our cost. So we went in early on and put in a very minimalistic demand control system that would count the pulses and would turn on a light in the facility, and that light would signal the furnace operators that they needed to turn down their power. We found it to be very ineffective. We stepped in with the advent of PLCs back in the early 80s to where we were able to put in a demand limiting program where we connected to the furnaces, and as we reached set points, we would start to reduce the power within the facility. We found that that really started to inhibit our capabilities to produce material as the facility expanded. So we started looking for a system that we could further reduce our charges, we could smooth out the operation, we could get better control that was closer to real time. I could use it for estimating utility costs for our accounting department, that we could look at metering loads by the line that they were connected to, something that we could use for reporting so that we could tell if we were saving money, and most importantly, a system that would not have impact to our production, that would give us a smoother operation. So we went down the road of looking at various systems. We looked at, would we do an in-house solution? Would we set something up with another PLC vendor? Could we utilize a Squared E product or an Allen Bradley product that was out there? And then most importantly, was there anybody that actually did foundry demand management? With that, we did find PowerIT Solutions, and we entered into a partnership with them to implement demand management. What we found with the platform that we chose is it gave us a very sophisticated control platform, and it gave us the ability to manage our utility costs through a very good program. So the automated demand control, basically what it's doing is it's helping us to predict through algorithms where our potential peak would be and to reduce the load on the furnaces and shift that melting into the next time period. All of you guys that are out there induction melting or coreless channel furnace melting or resistant heat type melting, I'll say, well, if you turn my power down, we can't produce metal. And you're absolutely right. Coreless induction melting, you produce with the current level of power supplies, you're producing roughly 4 pounds per kilowatt hour. So if you've got a 1,000 kilowatt power supply, you're producing roughly 4,000 pounds of material an hour with that. The software that, you know, we were looking at allowed us to go in and say, okay, if we can shift these loads, we could have a $5,000 per month savings by taking those peaks, shaving them off, and moving them out into another time period. So you can see how that shifted with the graph. Going into a more aggressive time period, this right here would be automated demand control. You can see changing over the course of the day the power levels and moving it down further to try to maintain a 2900 kW set point. In about 4 clocks in, you can see that it peaked at the 2,900 level, and then through the course of the day, things balanced out and smoothed out. It gives a precise, wide use of your power over time without having those great big high interrupting spikes that you pay for. So no load curtailment. Basically, your power comes in from the utility, goes through your meter, and it goes out into your industrial loads, and everybody uses all the power they want whenever they want, creating that coincidental peak. Under the automated demand response, the program is set up such that if you received a call, you would be running along, and for the response period, you would turn your power down and hit a controlled set point for your demand response timetable. In my case, what we did is we looked at and made the decision to go with the demand management software. It gave us the ability to set a control point that gave us 6.2 times the payback over 7 years. We had a real simple payback in 10 months. But interestingly, the power that we were able to save in the first year of operation was equivalent to the sales department going out and creating $1.7 million in incremental sales based upon the revenue that we were able to save. The accounting people, they like to bring things out over a net present value, and for the formula that our accounting department used, after a period of time, the net present value of that system was $293,000. And ultimately what we did is we decreased our peak electrical demand by 26%. You'll never get completely away from your peak demand because you're always going to have it because you're operating, but we were able to control it and reduce it by 26%. So here again, stepping through no load curtailment, you can see the large energy spikes. Configured load curtailment, you can see it comes in through the utility, through the meter. The SPARA demand management sits out on the network. It's looking at the equipment and what pieces are using the equipment, and then we have the ability to go out and control the loads and help manage the power. So the loads that are just being monitored and non-controlled, if they coincidentally come up and reach a full peak simultaneous with our induction power supplies, we could dial that induction power supply back for a couple minutes. Typically what would happen is we would see a large peak load coming in because of air compressors loading up. So during the time period when the air compressors would load up, we would dial the power supplies back, the air compressors would unload, and the power supplies would go back to full power. The SPARA Hub is a development through SPARA. It is a cloud-based system where the data is generated from the SPARA demand management system and then is stored up in the hub on the cloud versus having to have a local server. That system was brought in to help with the IT departments who would typically go out and move something on the server and cause an interruption in a system or the loss of data until they got the links reconnected. So by utilizing the cloud, the data is stored to a point where it's always going to the same location. Automatic dynamic pricing, time of use. Some of the facilities will operate based upon what it costs the utility. You can see that the pricing per megawatt hour is jumping all around. So with the automatic dynamic pricing feature of the SPARA system, you are able to set control points in there so that when that pricing exceeds $250 a kilowatt hour, you're able to set a control point that would be substantially lower than what you'd normally run at to help save money. You know, the demand management, reaching and having sustainable goals, you can do that through demand control. You can do it through dynamic pricing. You can do it through demand response, and then through energy efficiency. The SPARA product can interface and do all of those things. There's some financial benefits that can be derived. Typically, the system will pay for itself a minimum of 5 times over its useful life. Maximum savings can be 9 times what you may have paid for the system, and they do have some leasing options available. At Cannon Muskegon, what we found as we got in, we had 11 megawatts of connected load. On our furnace melting circuit, we were paying an $11 per kW demand charge. Without the demand management system in place, we had the capability of hitting $121,000 a month peak demand charge. By reducing our set point from 5.7 megawatts down to 4.5 megawatt, we had a savings of $58,000 per month through a reduced demand charge. You can say we went from $121,000 penalty down to $62,700 penalty. And, you know, that's a significant savings. You add that up on a monthly basis, and you have managed to save significant dollars. A typical comparison here, you can see the top slide shows no control. You can see things peaking up over 6,000 kW. You can see an older step limiter being brought in. We were able to hold a 5,000 kW set point. But what would happen is it was a multi-step program. So you would receive a demand step. It would reduce. You'd set at that level. You may reduce another one. And these steps were 30 seconds apart over a 15-minute period. Well, if you were reduced 5 or 6 steps because of the rate of power you were using, it would take 5 or 6 30-second periods to be able to recover, to be able to go back to full power. With the new foundry management system, we were actually able to reduce our set point lower, and we were able to do that because of the algorithm that looked at the power usage continuously, and it would determine if furnaces were turning down, it would automatically give that power back versus having to wait for the time periods to step back through and give the power back. So that was how we achieved the 26% increase in demand reduction. Here I'm going to show you some typical foundries. You can see this small-sized foundry. They were achieving loads over 1,000 kW, and through the addition of the demand control software, they were able to reduce their set point down to 835 kW. At the time this system was installed, they had roughly a 24-month payback, and they had a couple $1,000 savings per month. A medium-sized foundry that was operating up in the area of 3,800 kW, you can see that once the control software was put in during their on-time period, this was a facility that operated with a light. When they would be reaching the point that their counter would turn the light on, the operators were supposed to turn down their power to maintain a production level. And you can see in the top graph that they were successful most of the time, but it's that one orange 15-minute blip that they would have to pay their demand charge on. And once the demand management software was installed, you can see that they were able to hold a flat line at 2,400 kW, which offered them significant savings. Foundry that was operating with a peak demand around the clock, you can see their power usage was spiking throughout the course of the day. Once the set point was put in, they were able to maintain a flat level 4,800 kW, and they had significant savings of roughly $9,600 or $96,000 annually, so $8,000 per month. Significant foundry, a large coreless induction load. You can see that they were peaking at 19,000 kW, 19 megawatts. With the demand management software brought in, they were able to reduce that line down to 16,000 kW. And there again, you can see they had significant savings on a monthly basis and on an annual basis. So, proven solutions, a few of the foundries that are out there that PowerIT has worked with in the 1 to 3 ton range, 3 to 10 ton range, and greater than 10 ton. So some of the significant things that I experienced, I had a fairly rapid payback. I had an interface that was very easy to use and control. I purchased a product that had upgradable software and software support. I was able to have a holistic view of my entire facility, and I was able to get some predictability on my electrical bills. We were actually looking at the costing systems as we progressed through the month. Where were we for the day, where were we for the week, where were we for the month, and where we would be for the quarter from a financial standpoint. My monthly utility bills, once we installed the system and we were able to get some good numbers to work from, I was able to take the sales forecast for manufacturing and project for the accounting department what our monthly spend would be. I was able to project a $200,000 utility bill for electrical use for melting, roughly plus or minus about $1,500 on a $200,000 monthly spend. So we, with the automation that was there, we were able to get some accurate and real-time reporting that we could use from an accounting standpoint. The system was web-based, so we could look at it anywhere within the facility. So if we were having a meeting up in a front conference room, we could pull it up and look to see where things were at, how the furnaces were running, what kind of interference we had received due to demand control and demand management. That would allow us to forecast where we wanted to operate for the coming month based upon sales forecast. We may raise our set point number higher. We may lower the set point number based upon business climate and business conditions. It was a great visibility from a maintenance, safety, and training standpoint. We could track the number of kilowatt hours we were using to produce a heat. So if we were having an issue with a furnace, we could tell based upon the total number of kilowatt hours consumed, was there a problem downstream from the furnace? Did we have poor melting scrap? We could talk to the operators about why does it take third shift? Why can we produce 3 pounds per kilowatt hour while on second shift we were getting 3.4 pounds per kilowatt hour, or maybe third shift we were only getting 2 pounds per kilowatt hour. It would help us determine where our bottlenecks were in production. The other thing it would do is it's got the ability to send an email or a text message if we were going to exceed our set point. So we could, if there was a failure in the meter pulse, or if there was a failure, if we had a system lockout on one of the furnaces, because the system is designed such that if the PowerIT system has a failure in it, the furnace is still able to run, it would send us an email notification that we were exceeding or going to exceed our set point because we didn't have furnace control in place. The fellows out at PowerIT that I work with, Jared Burke, who did the introduction, and then Paul Van Avery, they can be reached. I'm going to turn this back over to Shannon, who has been tracking the questions and answers at this point in time. If there's any questions, please feel free to get them out to us.
Thanks, Dick. We do have a few questions that have come in. For the rest of you, if you do have a burning question, feel free to type it in now. There's still time. But we'll go ahead and get started with the ones that we have now. First, how do you ensure that production will not be impacted?
Jared, are you there?
Yes, I'm here.
Shannon asked the question, PowerIT Solutions, how do they ensure that production won't be impacted?
Yeah, it's a great question. So with our technology, SPARA Demand Manager, as Dick's been speaking about, it's a software and hardware-based solution, and within that we allow our customers to put as many rules and constraints into the system to maintain production needs. So those can be any types of constraints around time, around temperature, really anything that can be monitored and put into the system. Our technology will never break those rules. So even if, at the expense of, energy savings, our system's always going to make sure that production needs are met.
Great. Dick, did you have anything else to add, or should we move on?
Well, I found that with those rules, we were very, like I spoke during the talk, we were able to look at our sales forecast, and we could project and move our set point line up and down. And it was very typical that we were within 1 or 2 or 3 kW of our set point. So we could adjust as manufacturing requirements went up. We could increase our power level and still maintain a control point and still meet all of our production needs.
Okay. Our next question was, does the system improve energy efficiency, and if so, how?
I didn't recognize a lot of energy efficiency improvement because the power supplies are utilizing power at a given rate. As I said, typically the coreless induction power supplies of today's technologies are operating at roughly 4 pounds per kilowatt hour. But where we did find some energy efficiencies was by the ability to track how much power each furnace was using for each heat that we manufactured. When we first started out for a 10,000 pound heat, we would find ourselves using anywhere from 2,700 kilowatt hours out through maybe 3,000. As we got better at operating the furnaces and having ladles ready to move the metal and meeting the production requirements, we found that we were able to drive the total number of kilowatt hours used per heat, from that 2,800 number down closer to the 2,500 kW number. Typically, we would, after our operators got experienced with paying attention to the system, ladle operators making sure that the ladles were ready to go, things of that nature, we would typically see power usage of about 2,600 kilowatt hours, which was a lot closer to our 10,000 pounds of material we were producing an hour. So we achieved some efficiencies through better management and better coordination within the facility.
Okay, thank you. Next we have, will my production be impacted if the demand control system goes offline?
And I addressed that a little bit during our speech. The system is designed that if the demand management system fails, it allows your furnace to be operated just like it was prior to the system being installed. So you lose the ability to manage your peak demand level, but you don't shut your operation down. So if the system were to fail during the middle of the night and you couldn't get it back up and operating, you would be able to still continue to meet production demands and production requirements. You would just end up having to pay a higher penalty at the end of the month if you set a coincidental peak in your facility during that time period.
Yeah, this is Jared. Just to chime in there, with our technology and with our platform, we really have it in a fail-safe situation, so that if the SPAR system was to have a problem, all controlled loads would still be able to be utilized for production needs and to keep the operations going.
Okay, let's see here. The next question is, what if I have a production need that requires me to exceed a predetermined set point? Will the system still be able to provide savings following that event?
The system would, if you have production needs that require you to go to a higher set point, what will happen, because your demand charge is set typically on a monthly basis, you would be able to raise your set point. Let's say if you're operating at 2,000 kW, you could raise your set point to 2,500 kW and get out those production requirements. And then as you came to the end of the month, your billing cycle, what you would do then is you would go back in and lower that set point down to 2,000. Because with the utilities, they are going to charge you that peak demand charge based upon the highest occurrence during your billing demand cycle for that month. So once you set it, if you've reached that point, you might as well continue to operate there based upon your production, because you're still, it goes back to the kilowatt hours you need to use to produce your material for the month. It's the penalty for the demand charge is based upon how fast you use those kilowatt hours. Well, once you've established that high set point for the month, you might as well have that available for the entire month, but prior to the start of your next billing month, if you lower it back down, then that coming month you will have the ability to save that demand charge based upon your production levels being at a lower level.
Yeah, if I can add something else to that, Dick, that's a great question and something we've thought about quite a bit. And one of the things that we've actually introduced into our SPARA technology is something that we call an adaptive set point. And what we do with this is we allow our customers to create a peak demand set point early in the month, and as their production requirements require them to set a higher peak above that set point that they started with, our system naturally starts to adjust and increase the set point for them. So that way our customers are able to start off the month and be very aggressive with their peak demand control capabilities and allow the system to really fine-tune and find the right and ideal set point for them. At the end of the month, our system will then reset to that earlier set point or that more aggressive place. And so many of our customers are able to use that functionality to increase their savings and really get the best and find the most optimal position for their demand control set point.
Thanks. And it looks like our last question we have is, my utility doesn't currently offer DR programs. In the event that they are added in the future, will my system allow me to participate easily without additional costs or upgrades?
Jared?
Yeah, absolutely. So our system is really designed for our customers to grow and change. All you guys who are, running large industrial facilities know that you're constantly changing things, moving equipment around within the facility or bringing on and off loads. So our system is really designed to grow with you. When you have something that you need to change, you can just tie that system into our software platform, and then remotely we can do some minor adjustments and bring those loads into the system. So many of our customers have added loads or expanded the scope and the footprint of the SPARA demand management system over time. So I know the question was more around demand response, and I'm talking about loads. Our platform, as Dick has spoken about earlier, we have the demand control capabilities to affect peak demand charges. We have our demand response algorithms so that if you have these programs, you can curtail based on these utility programs. And then we've got the dynamic pricing or the real-time pricing functionality as well. Our customers may be purchasing our system today for peak demand or for real-time pricing mitigation, and over time those things change. Our system is really designed and has all the functionality in the software, so as things change, they can enable or turn on and off different aspects of the software platform. So it future-proofs our customers so that as these new demand response programs or new utility programs are rolled out, they're able and ready to immediately capitalize on using the SPARA system to reduce those costs.
Right, and I can add to that, Jared.
Sure.
I actually had to, when we originally installed the system, we did not have demand response available to us. The original system went in on 2 air melt furnaces and 2 vacuum furnaces. We added 2 additional loads as the facility grew, and it was very easy to incorporate those 2 new furnaces and power supplies into the system. And when the demand management for interruptible power came along, we were very easily able to add in the demand interruptible power. In our case, the notification for the interruptible power would come through an email, and it would give us 15 minutes to respond to that. And I was the primary point of contact. Well, if I happen to be out of the plant or away, it would be difficult for me to enact the demand response portion of the program. In working with you guys, you were able to set up a dial-in telephone switch that if I received the email notification that we needed to interrupt power, I could go in through a phone call and go in and set the system up so that it would go into the demand response mode at the correct time, and then I could notify the management group at the plant that, let's say at 8:30 I received an email saying that at 9 o'clock we were going to have to be at our interruptible power set point, where we would be turning from 4,000 kW down to 2,500 kW. I would set up the program that at 9 o'clock we went to the 2,500 kW set point. The furnaces would be managed and controlled at that level, and then I could contact my counterparts at the plant to let them know that at 9 o'clock, not to panic, but they would be operating at 2,500 kW versus 4,000. And it was virtually seamless. It worked very well. And that was added after the original system was installed.
All right. Well, it looks like that was the last of our questions. I want to thank you, Dick and Jared, again for presenting the webinar, and to everyone else who took some time out of their day to attend. Have a wonderful rest of your Wednesday.
Okay. Thank you.
Thank you very much, everyone. Appreciate it.